So good to start. You are.
Okay.
All right. So thank you everybody for coming. That's awesome. And also really sincerely thanks for coming to support Max as well. I think people really appreciate it when they get to share their work with others and not just the committee. So I want to introduce Max Siebersma, who has been researching in my research group for a couple, maybe 3 years now.
3 years. Yeah.
And has been working, as you will see, very hard on trying to make sense of polymer quantum mechanics and actually doing something useful with it. So looking forward to his talk. I guess if it's not obvious, this is Max's defense of his senior honors thesis. And if you want the shorter version of it, he'll be presenting again a condensed version of this talk, actually defending for just the physics department's thesis, and that's in 1 to 2 years.
Yeah, during finals week.
Yeah. All right, great. So if you want to recap, we'll get an opportunity to see it then. So otherwise, your show.
All right. Thank you so much, Dr. Craig. And thank you also to all the committee members for being here and reading through my thesis. So without further ado, I will be talking about my honors thesis on the particle on a ring in polymer quantum mechanics, a quantum cosmology analog on compact space. Okay, that's a bit of an issue if my slideshow doesn't work.
On Zoom as well?
Yeah, we do.
Great.
Is it showing up on Zoom?
Yeah.
Okay. I guess clicking works. I will do that then. Okay, so just to provide a quick overview of what I'm going to be talking about today. I'm going to start by introducing some of the major concepts and motivations that are important for polymer quantum mechanics. I'm going to explain some of the mathematical background that you need to understand the theory, specifically related to topology. I'm going to explain the main mathematical framework that underlies polymer quantization and some of the results we get from that. And I'm going to use that to talk about a particle on a ring, a new physical system that hasn't been solved to my knowledge until now, and how we can get back to ordinary quantum mechanics in a continuum limit. So the motivation behind polymer quantum mechanics ultimately stems from the problem of quantum gravity. So we have two physical theories, general relativity, which describes gravity, and quantum mechanics, which describes small stuff, which both work really well in their own respective regimes. But for the past 100 years or so, we haven't been able to fit them together in a way that we can test. And in general, there's a lot of mathematical difficulties with that. But one theoretical framework that attempts to reconcile them is called loop quantum gravity. And in this framework, we get space time becoming these discrete chunks, roughly speaking. Now, polymer quantum mechanics was motivated by some of these ideas in loop quantum gravity, but it looks at just kind of quantum mechanical systems we're more familiar with and are a lot easier to work with. So when we talk about quantizing a system, what we're really referring to is trying to go from a classical mechanical mathematical understanding to a quantum mechanical one. So in classical mechanics, we have variables like position and momentum that form coordinates in what's called phase space. And we can relate these with an algebraic structure called a Poisson bracket. And in canonical quantization, we map this bracket to a commutator relation on operators, and we get what's called the canonical commutation relations. Now, a question that comes up with this is there any different way that we can express what this quantization looks like on physical systems? And there's a mathematical result called the Stone-von Neumann theorem, which places some pretty strong restrictions on how we can do that. and we'll talk about it a bit more later. So more specifically than just loop quantum gravity, polymer quantum mechanics came from a theory called loop quantum cosmology. Loop quantum gravity in its full generality, very complicated, but we can look at more symmetric models to try to piece together what's going on. And so we look at this homogeneous isotropic model of the universe where everything gets kind of smeared out. So each of these sheets that's portrayed in this picture is all of space at some instance in time. And we foliate along these space-like slices with a time variable. The main variables we get in this theory are called the triad flux and the connection, which are pretty fancy sounding names, but the triad flux basically corresponds to a volume element of space, and the connection tells us how we take derivatives on these slices. When we quantize this model, we find that the triad flux is discretized and the connection is no longer well defined. Now, taking it to an even more familiar context, we can think about the relations in loop quantum cosmology like the relations we get in like simple point particle quantum systems. So the position we can think of as becoming discrete, and its conjugate variable, the momentum, is not well defined, similarly to the case we get in quantum cosmology. And further, in quantum cosmology, we can take an exponentiated version of the connection called the holonomy, which is well defined. And this more or less corresponds to integrals around loops, hence the loop quantum name. And we'll do something similar in this point particle model where we get something called the Weyl operators. So polymer quantization basically is a different method of quantizing a system than what we see in ordinary like classroom quantum mechanics, which I'm going to call Schrodinger quantum mechanics. And it uses these quantization ideas from quantum cosmology. And importantly, it bypasses some of the assumptions of the Stone-von Neumann theorem, giving us distinct results physically. And so the main idea that we get from polymer quantization is instead of having this continuous space you can move along on, we end up with this discrete space. And just because I know the question will probably come up when we talk about polymers, we're not talking about organic macromolecules. The polymer-like structure comes from the fact that we end up getting this lattice on our space, and our wave functions are these excitations that look like this. And I guess at some point in time, someone thought that that looked like a polymer, and the name stuck. So I obviously can't go through all of the math that you're going to need to understand polymer quantum mechanics in one sitting, but I believe that the most important ideas that we need for this discussion come from topology, which is the mathematical study of open sets. And we can use open sets to talk about what the overall structure of a space looks like and generalize some familiar concepts from calculus, like continuity. So within the toolbox of open sets, I'm going to go through some of the tools I use in my thesis. To begin, just as a, I guess, so you know what I'm talking about when I use topology as a noun, a topological space is some set that we define a topology on, and the topology is the collection of all of the open sets within that set, all the open subsets really. So what the topology does is it defines which sets are open. Like in this image I have here, it's a really simple topological space with just 3 points. And all of these colored ellipses are supposed to represent what the open sets are. So like A and C are together in an open set, where A on its own is just an open set. And all of those ellipses together is the topology. So one concept that we can generalize using open sets is limit points, which you might have heard of in calculus a little bit. And these are points within some set A in the topological space where every open neighborhood intersects with another point of A. So if we have some point and we take an open set that that point is in, it's always going to intersect with our set A. So we can, even though we're not really talking about distances, we can think of limit points as being close to the set A. On the other hand, there are isolated points, and this is kind of the opposite case where we can find an open neighborhood to isolate them in. So like these singleton ones out here, all living on their own, no neighbors to speak of. And limit points don't necessarily need to be elements of the space, but we can take, or they don't have to be elements of the set A, but we can break up the set A into limit points and isolated points. Within the set, it's going to be one or the other based on how we can isolate things in neighborhoods. Now, homeomorphisms are one of the most important ideas that I'm going to use in this talk. And these come from a generalization of continuous functions. So if the function is continuous, then all of the open sets are mapped to from open sets. So like space X, we have a function to space Y. If we have an open set in space Y, it better be mapped from some open set in X. Homeomorphisms are bijective, so one-to-one onto functions between spaces that are continuous in both directions. And what this means is that the open sets are going to always get mapped cleanly to new open sets in both directions. So we can talk about the topologies as equivalent. And if you've heard about topology just a little bit before, you're maybe familiar with this example slash joke that topologists can't tell the difference between a mug and a donut. And that's because there's a homeomorphism that goes between them. So like if I have a donut, which I have out of modeling clay here, I can kind of deform it, and all of these deformations are functions which preserve open sets. And if I keep on molding it, I can eventually get it into this mug shape, and that's homeomorphic. But if I did something like break the handle, all of these open sets that lived right here are no longer mapped to other open sets. So not a homeomorphism once we do this. The main, oh, not yet. Okay, compact spaces are another concept that's important here. And compact spaces are defined by things called open covers. So if you take a bunch of open sets and you cover some given set with them, that's an open cover. And compact sets are ones where there's always a finite subcover. So if Miranda was to give me an infinite number of open sets, but it covered a compact space, I could always go through and find some finite number that does the trick just as well. In Euclidean spaces, like the one we're in right now, this definition is equivalent to closed and bounded sets. So things like closed interval of the real line or a circle. And an important theorem is the Bolzano-Weierstrass property, which says that an infinite subset of a compact space must possess a limit point. So if I took like a circle, which is a compact set, and I picked an infinite number of points on that circle, under a standard topology where it's compact, I'm always going to have some limit point in that choice of points. Now, the main topology I work with in this thesis, or at least probably the most important one, is the discrete topology. And on any space, you can just say, okay, I want my topology to be every single subset of the space. And that is called the discrete topology. So that also means that every singleton point is an open set, which means that they're all isolated points because you can always isolate them in neighborhoods. And also, because everything's open, all functions from discrete topologies have the same cardinal or have all those functions are continuous. If two spaces are the same cardinality, so the same number of points, because these functions are continuous, if we give them both discrete topologies, they're going to be homeomorphic. So like if I took the real line with a discrete topology, there's no real way to talk about any points as being close to each other. The real numbers are kind of just labels. So I can have the freedom to rearrange those isolated points how I wish, and that's a homeomorphism. Now, moving on to some stuff that's more directly related to quantum mechanics, we can exponentiate our position and momentum operators to get what I'm calling the Weyl operators. So a complex exponential form of position and momentum, and those are unitary operators. And these operators inherit the commutation relations that I talked about previously between position and momentum, which are summarized up in this box here. So same algebraic structure, but also all we have right now is algebraic structure. We're in abstract algebra land, and we want to go to linear algebra land, so we can do things like act on vector spaces, which is very useful in physics and quantum mechanics in particular. So what we're doing is finding a representation of this algebraic relations on a vector space. What the Stone-von Neumann theorem tells us is that assuming we meet some basic criteria, whichever way we try to do this, we're going to end up with a representation that's the same as Schrodinger quantum mechanics. What we want to do is find some different path that doesn't get sucked up into the Stone-von Neumann theorem that gives us a completely different representation. So trying to find this narrow path that doesn't get sucked up into here. And so the way that past physicists did this is to break the weak continuity condition of the theorem. So the theorem assumes that this limit is true for the Weyl operators. And so we get around it by defining this orthonormal basis labeled with real numbers mu. And because it's orthonormal, whichever real numbers are in it, the inner product, if they're different, is going to go to 0. And if they're the same, it's going to go to 1. So what we do is we relate the Weyl operators to these kets on the vector space by having them shift this index mu, or I don't know if index is the right word, but the label mu. And in doing so, we make it so this limit that we assumed for the Stone-von Neumann theorem is not true. So weak continuity does not hold. We have a new representation, and also because V, which is related to momentum, is not weakly continuous, we can't exponentiate some operator to get to it. So momentum itself is not a well-defined operator anymore. So I'm not going to go through all of the math, but just here's like a quick summary of some of the main results in polymer quantization. We have plane waves corresponding to momentum wave functions and Kronecker deltas corresponding to position wave functions. And also, when you use the Weyl operator V on these states, it shifts the label mu by whatever its parameter is. So shifting it by lambda visualized here. And position operators, or the position operator, pulls out that value of mu. So it acts as a labeling operator. And by this construction, you can kind of see that our abstract mu states actually correspond to position eigenstates. Now, to do quantum mechanics, we also need to think about things like inner products. And inner products typically require integrals. And to have our integrals be well defined, we need to be clear on what our topologies are. And so the topologies we get in polymer quantum mechanics are not the standard real line with Lebesgue integration on it. Instead, we get for momentum what's called the Bohr compactification of the real line. And this is a real kind of exotic space that I don't have time to get into. But something that's known about the Borg compactification is that when you take a Fourier transform of it, you get to the discrete real line. And we put a counting measure on the discrete real line to do our inner products. So position has a discrete topology now. And also because our wave functions are Kronecker deltas, what this counting measure tells us is that if we take the integral over one of those functions, it goes to 1 now instead. So it like counts the number of points with a given value when taking integrals. Normally, like those Kronecker delta functions, they would integrate to 0 because it's just discontinuity at a single point, but that's not how things work in the counting measure. And because of this way the inner products work, we can think about labeling our position eigenstates, those eigenfunctions, with just a ket. We need a little more structure, though, to be able to do quantum mechanics in this framework. And this comes in the form of defining a graph on our position space. So specifically, we take a countable number of points on the real line. And one of the rules for choosing these points is that if you think about the real line with its standard topology, we can't pick any limit points. So none of this stuff. And in doing so, that means that all of the points that we pick are isolated within that set. And so this graph we build has the discrete topology, which is what we want to see from our construction. And also, discrete topologies, as we recall, are homeomorphic. So we can just rearrange these points into a regularized lattice with this constant spacing mu naught. And we can think about this new mu naught parameter as something like a minimum fundamental distance. So like smallest distance in space that's allowed. And also by regularizing it, we restrict ourselves to Weyl operators that only shift us along the graph by integer values of this parameter mu naught. One last thing we need to do for physics' sake is approximate momentum, because we'd like to do something dynamical on our system, but the kinetic energy in the term in the Hamiltonian requires this p squared term. So we ought to do something about that. And we can approximate this term using operators which are well defined, namely the Weyl operators. So to walk you through this process, all of you paradigm students should be kind of acquainted with the steps I'm going to take. Maybe you wouldn't guess to do them in this order, but first, our momentum variable can be related to the Weyl operators through this complex exponential. And so we can use Euler's formula to take our Weyl operators and put them in a form that's like cosine. Next, we can take a Taylor series expansion, and out of that cosine, if we truncate the series at some term, we can get a p squared term out of that. So things are looking good so far. And by rearranging what we have here, we can make an approximate p squared operator out of these Weyl operators that shifts us on lattice points in the system. So now we have all of the tools we need to talk about the particle on a ring, but we are now going into uncharted waters here. So to start with what we know, the ring as a topological space is the circle denoted S1. And we can really just think about it as taking this real interval with a periodic boundary condition on it. But as we go through the process of polymer quantization, we don't change anything about the momentum. So that aspect stays the same. And what we get is also that we find a discrete topology on this interval on the real line. The same discrete topology, in fact, as we find not when looking at the ring, but looking at the entire real line. And that's because both cases have the same cardinality of points, an uncountably infinite number, both have discrete topologies. They're homeomorphic to each other. So we have this discrete topology, but because of how our Weyl operators act as shifting operators on our system, we can still use those to get back to a sense of periodic boundary conditions. Namely, that if you use the Weyl operator on a position eigenstate enough times, you will shift it all the way back around to its original point. And another important thing is the Bolzano-Weierstrass property, which we talked about earlier, guarantees that if we are on a compact space and we're not allowing limit points, then we must have a finite number of points. So when we build our graph on the ring, we don't just have this new parameter mu naught, but also a number of points n that describes our system. So you have a finite number of allowed points on the ring. And so our wave functions can be expressed as finite sums of position eigenkets. And this gets us to the crux of the problem, which is solving the time-independent Schrodinger equation or the energy eigenvalue equation. And just to break down what's happening here, we have the identity operator, which acts pretty boringly, the Weyl operators, which shift our states and also carry that periodic boundary condition on them. And we're expressing our eigenstates in the position basis. So although it's only about a slide, this was a step I was kind of stuck on for like a month. And one of the big problems I had with it was trying to relate those shifting operators to recurrence relations. But what I eventually realized was a better way to think about it is considering the properties of the Weyl operators with that periodic boundary condition. So if we operate the shifting operator by a lattice site n times, we get all the way back around to the beginning of our ring. And if we think about our Hamiltonian in matrix form, those Weyl operators correspond to these off-diagonal ones that wrap back around to the corner over here. And the reason I'm showing this is for the benefit of you who took periodic systems, and you might recognize this form of matrix. This corresponds to the symmetrizing operators on a coupled ring of oscillator systems. And what you might remember from that, and you can also just find it algebraically using the V of mu naught operator, is that the eigenvalues of those submatrices are the complex roots of unity. So the nth roots of one on the complex unit circle. It's like, here's the third roots of unity in the complex plane. And so with that, I was able to find the energy eigenvalues and eigenstates of the particle on a ring in polymer quantum mechanics. And we have this quantum number lowercase n, which corresponds to the number of complex roots of unity. So there's going to be a different energy state for each complex root of unity. And so you can kind of visualize it. Keep in mind that our functions are like Kronecker deltas, now defined like with complex scalars. So putting them on the ring, this is a system with 10 points, and you can kind of see the Kronecker delta nature. As we increase the number of points, this starts looking more like a sinusoidal graph, which is kind of what we hope to be seeing in like normal Schrodinger quantum mechanics. This is starting to look like those eigenstates. And so this brings us to the last big question. Do we get the continuum limit back when we look at this polymer quantum system? So as Oksana or any other experimentalist in the room will tell you, the results that we get from the quantum mechanics we know and love, Schrodinger quantum mechanics, works really well in experiments. And so if polymer quantum mechanics is to be anything physically useful or interesting, those effects have to take place in a regime that's too small for us to measure. So you have to be able to take that discretization and have it go to zero and have results that get back to what we would expect in Schrodinger quantum mechanics. That's the main idea behind the continuum limit. Mathematically, that corresponds to taking these energy equations and eigenstate equations that I derived, and something related to taking the limit as mu naught goes to zero on them. But if you just try and do this naively, like I did at first, you run into some problems, like those energies will diverge, and this doesn't even have any mu naughts in it. Another issue is that there's nothing that corresponds to a physical radius in my construction of the ring. If you recall, I just took a section of the real line and put periodic boundary conditions on it. But we can relate them together with the circumference of the ring. So circumference of a circle is 2 pi r. And if we think of mu naught as a physical distance, the radius of the ring is n mu naught. So although in the polymer case, there's not like a physical radius we're talking about, like we're not working in 2 dimensions or anything, we would expect that sort of like Euclidean geometry to come out in a continuum limit where we do have the circumference of the circle is 2 pi times its radius. So using that to redefine our energy levels, we can now take a limit as mu naught goes to zero, or more explicitly, mu naught over r goes to zero. And that's really to emphasize, we're not just looking as our distance parameter goes to zero, because otherwise we're just making a really tiny ring, but we're looking at the discretization becoming very small with respect to the size of the ring itself. So if we Taylor expand the cosine function and regroup some things together, all of those higher order terms with mu naught over r's go to zero, and we get the expected energy level results for the particle on the ring. And this is a graph that shows how that continuum limit comes about. So these red lines are the polymer energy levels, and the blue lines are the Schrodinger energy levels. And so as we take the limit as mu naught over r goes to zero, you see the polymer energy levels gradually get closer and closer to what we expect from Schrodinger quantum mechanics. And to comment on what these green lines mean, each of those represents an allowable ring with endpoints, because we can only have an integer number of points on a ring. And so, yeah, the actual only energy levels you see are where the green lines intersect with red lines on this plot. But I tried plotting that and it looked really terrible. So we're sticking with this interpretation. And also, the energy levels truncate because this quantum number n is less than or equal to the number of points on the ring. And that ultimately stems from the fact that our number of eigenstates is given by the number of roots of unity, or there's that correspondence. Finally, we can also see that as mu naught over r goes to zero, the allowable ring sizes, I guess, like this spacing of ring size A minus ring size B goes to zero in the continuum limit, which is what we would expect to see from the discrete space approaching a continuum. That's the blob of green lines at the end. Wave functions are a bit of a trickier case, though, because recall that we're talking about like Kronecker delta functions defined on a graph with this counting measure on it. And although like the waveforms do kind of look sinusoidal, how do we get from this Kronecker delta case on the left to this continuous case that we see on the right? And what some previous authors who I've cited here were able to figure out is that there's a way that you can go about rethinking what the position space wave functions look like in a way that is equivalent to the way that we're showing them with Kronecker deltas. So in this redefinition, we take our Kronecker deltas and turn them into step functions. So they're defined at the same as the same value at each lattice point up to some normalization constant, and then you just increase the step across the next lattice point. The normalization comes from the fact that the counting measure and the Lebesgue measure don't yield the same things. So over this, on the left, counting measure integral, each of those terms integrates to 1, but you're kind of restricted by what the spacing between lattice points is on the continuum case. So we renormalize the values of the functions to get the same inner products in both cases. So using this redefinition, I was able to prove that the continuum limit holds for wave functions as well. So on each lattice site, the Polymer wave functions and the Schrodinger wave functions become exactly equal to each other. And as we take the limit as the lattice spacing goes to 0, we're going to get more and more points. And so the intervals that these Polymer functions are defined on get smaller and smaller. And because the Schrodinger wave functions are just these nice, simple e to the ix uniformly convergent functions, that means that as we make these intervals smaller, the deviation also does. So we see that our Polymer wave functions converge to the Schrodinger wave functions in the continuum limit. So the lattice spacing gets smaller, and so does the deviation between the functions. Like you all in the back might not even be able to see that these bottom graphs are made of step functions. And that's really what the continuum limit is all about. If you're standing far enough away, you can't tell the difference. So just to summarize everything I've done, I provided a pretty comprehensive overview in my thesis of polymer quantum mechanics and all of the math and a lot of the calculations you need to build it up. And using all of that, I was able to solve for the energy eigenvalues and eigenstates of the particle on a ring system, which to my knowledge has not been done before. So pretty exciting to have a new quantum system that we can analyze. And also we have the surprising result that due to the fact that the ring is a compact system, we have that finite number of points on it. And so we also get a finite energy spectrum, which is not something we see on the Schrodinger ring. So qualitatively, kind of a different result, which is interesting. But I also showed that in the continuum limit, for this specific case of the ring, the eigenvalues and eigenvectors do converge to what we expect from the Schrodinger theory. So some questions that were led to for the future are different ways that we could maybe generalize these results. For example, we've done a ring. Is it possible to do a sphere? It's possible, maybe, but also adding another dimension creates some difficulties with the lattice. So there's open questions there. And also we know that polymer quantum mechanics is this analog to loop quantum cosmology, and the ring is this compact system we now have solved. So maybe there's some correspondence between this ring case and a compact model in loop quantum cosmology. It's also entirely possible that that's not the case at all, because quantum cosmology has a lot more intricacies and difficulties. But that's a question for the future. And also, I just like to say that this work was not done in a vacuum. I've been working with Basie Cyber in analyzing polymer quantum mechanics. So next week, I don't know if the date did or did not get changed. Don't know, but she.
Yeah, but apparently there's like a mandatory staff meeting or something.
Oh, that's new.
Yeah, so I'm gonna talk with her.
Well, regardless, you should not miss her talk. It's going to be excellent, and she's going to talk about polymer quantum mechanics and time evolving these states that I found here. Thank you.
Okay, so this is a defense. So this is the point in the process where you all get to ask Max any questions that you have. So after we spend some time, Max spent some time to answering questions. At that point, thank you very much for your attendance, and then the committee will get a chance to ask their own questions of Max, and we'll go on from there. So open the floor to questions.
And basically you're on Zoom, so I guess if you're in Zoom, maybe you could put a question in the chat and basically can raise her hand on your behalf. Yeah, Joey.
So when you were talking about the discrete topology and how you analyzed it initially, and you were talking about how it was like homeomorphic, however you wanted to arrange like the spacing of the spots in the ring. And then towards the end, when you started talking about how you get the continuum limit, you use the step function instead of the discrete counting measure. Is there some, I don't really know a ton about topology, but is there some notion or like, are there any special considerations you need to make that like, it doesn't really seem like if you go to that step function thing, you have that same topological invariance of like how depending on you stuff around. So
Yeah.
there's some justification for doing that, I guess.
Well, yeah, part of that comes from building the graph. So actually in constructing the graph of positions, you start with the real line and its standard topology. And by choosing points on it, what you get is called an induced topology. And that induced topology also takes on a discrete characteristic. So part of it is we're starting with the real line and then inducing a discrete topology on it and then regularizing into a lattice. Another consideration to make is that the Weyl operators still act on positions, and they act in this very algebraic way, which gives structure to the position space. And so ultimately what we get is like from a pure quantization standpoint, like just starting from the mu kets, which are called, they build what are called cylindrical states. You get, starting with those, you just get like this kind of abstract version of the discrete topology, but by putting physical structure on it, we get back to something that's kind of closer to the structure of the real line with a standard topology. And that's through the process of like building this graph and having the Weyl operators defined on it. I don't know if that answers your question.
I think you do that.
Okay. Yeah. Perfect.
I don't remember exactly where it was, and I'm not familiar with a lot of this physics, but you mentioned truncating the Taylor series for one of your functions, and I'm wondering, like, does that have any consequences? Or like, what if you had truncated it at a different place? Would your method still work?
Do you remember what I was talking about? Was that dynamics or was that in taking a continuum limit?
That wasn't approximating the square.
Oh, okay. Yeah, that actually is pretty, that's a great question. And that is kind of significant. Okay, so is it this Taylor series? Yeah, so in taking this Taylor series, that's why it's an approximated momentum operator. And this Taylor series approximation is not this exact cosine function. So this momentum operator is not equivalent to our the actual momentum operator. And in taking this truncation, the assumption that you're making is that the whatever variable corresponds to your classical momentum P is much, much less than h bar Planck's constant divided by mu naught. And so one piece of that assumption is that we're assuming that mu naught is a very small quantity, which is corresponds well physically to thinking about it as this like minimum spacing. Also, what that means is because you're assuming P is small, it's really a low energy approximation that we're working with because our energy comes from P squared over 2m. So in very high energy cases, we wouldn't expect this to be an approximate momentum operator. And that low energy comes from comparing it to Planck's constant divided by mu naught.
Other question, just happen to be on this slide.
Okay.
There's this issue with not having a momentum operator, so you do this approximation squared.
Mhm.
If you wanted P, could you just use the sign?
Yeah, so that's actually, so a lot of the literature, the way they do it is they first define an approximate P operator using sign. If you square that, then you do get something that approximates P squared, but it has the unfortunate side effect that these are not V of mu naughts, they're V of 2 mu naughts. So they move you by 2 lattice points instead. And yeah, so it's more convenient to just have our lattice size be our lattice size, and have shifting of one space. Logan?
I think the nonsense is for like particle scale. You said P squared over 2m should be small. So do really small masses.
I'm not certain about that. I mean, mostly what the restriction is on P, so I don't believe it would. I guess just in general, the things that polymer quantum mechanics assumes put some restrictions on it that make it so that it would not be quite like what we would expect to see in like a quantum gravity case. For example, it's not Lorentz invariant at all. So if you have anything that's going marginally close to the speed of light, that's a no-go. Polymer quantum mechanics will not do you well.
Do you have other questions from the audience? Okay, thank you so much, everyone, for coming. Let's thank Max again.